Hello, teacher, classmates, and assistant. Our topic is elliptic curve cryptography. Our team is composed by Andres, Sergio, Jerome, and Sergio Zúñiga. And we're going to start with the topic. We're going to go with the index, which is going to be concepts, advantages, and disadvantages, ECC versus RSA, when to use it, recommendations, and specific uses. To begin with, we would have to explain what is ECC, or elliptic curve cryptography. Well, it is a branch of public key cryptography that uses the mathematics of elliptic curves to provide secure communication and data encryption. It also offers some advantages over other forms of cryptography that we will go over in the next slides. It also includes smaller key sizes and faster computations with a high level of security. Then we also have some important concepts that we are going to go over with. First of all is the elliptic curve and the points of the elliptic curves, which is, the elliptic curve cryptography is based on the properties of elliptic curves over infinite fields. These elliptic curves are defined by this equation that we can see here: y power to 2 equals x power 3 plus ax plus b, where b and a are constants and the curve has certain algebraic properties that make it suitable for cryptographic operations. And it also has some points that satisfy this equation. Then we have the discrete logarithm problems, which is where the security of the ECC relies on the difficulty of solving these logarithm problems, which is going to give a point on the curve and a scalar, with each computationally difficult to determine the value of n when p and where g is a known point. Then we have public and private keys that we've covered on previous classes. But there are secure keys to exchange protocols, such as Diffie-Hellman key exchange or elliptical Diffie-Hellman. And two parties can exchange their public keys, perform calculations, and use their private keys to generate a shared secret key without exposing any private information. Then we have digital signatures, which can be used as algorithms such as the elliptic curve digital signature algorithm, which is a private key holder can sign a message using their private key, and anyone with a public key can verify the signature. Then we have key sizes and security, which this is just an example. It contains a 256-bit ECC key, which offers a comparable security to a 3072-bit RSA key. So it makes it more efficient in terms of computation, storage, and bandwidth. And there are some standardized ECC curves for cryptographics, such as NIST curves and curve 25519, which have been extensively studied and analyzed to ensure security. The way it works, first you have to generate these are some additional concepts that we might go over at the very end. And the important part is how it works. It first generates a key. Each user has to generate a pair of cryptographic keys, the ones we mentioned before, the public and the private keys. And the private key is a random scalar from a specific range. Then you have to select the elliptic curve, which is chosen for cryptographic operations. The most commonly used include those standardized by organizations such like NIST, and the curve parameters such as the curve equation and the base point are public and shared. Then we compute the public key. The public key is generated by performing a scalar multiplication of the base point on the chosen curve by the private key, and it is computed as p equals dg, the resulting point of these curves, become the public key associated with the private key. Then we have the key exchange or encryption, which ECC can be used for exchange or encryption purposes. As I mentioned before, in this case, the key of exchange, two parties exchange their public keys and then they use their respective private keys to perform calculations that generate a shared secret key. And this can be used for symmetric encryption. Then we have the digital signatures. such as the elliptic curve digital signature that I mentioned before. And finally, the security is based on the difficulty of solving the discrete logarithm problem on elliptic curves. It is important to know that these elliptic curve cryptography operations involve modular and arithmetic point additions on the elliptic curve. They are carefully designed to ensure security and efficiency of these algorithms.
Okay, so now we're going to see some of the advantages of ECC. Well, first, we have a strong security because it provides a high level of security with small key sizes compared to other encryption algorithms. This makes it more efficient in terms of computational resources required for encryption and decryption. Then we have faster performance. Well, this is due to the smaller key sizes. The operations generally require fewer computational resources and less bandwidth. This leads to a faster encryption and decryption speeds. Also have bandwidth efficiency, which will ECC's compact key sizes also contribute to lower bandwidth usage. And then we have strong resistance to attacks. Well, ECC has proven to be highly resistant to various cryptographic attacks, including those based on integer factorization. It provides a robust level of security against both classical and quantum computer attacks. Let's go to the next. Thank you. So now we have the disadvantages. Well, first, the implementation complexity. Well, this implementing ECC correctly requires expertise and attention to detail. Errors or vulnerabilities in the implementation can undetermine the security of the entire system. Patented algorithms. Some specific ECC algorithms were patented in the past, which could affect their adoption due to licensing concerns. Then we have the key management, which, like any other public key cryptography algorithm, ECC requires proper key management practices. The generation, storage, and distribution of the keys need to be carefully handled to maintain the security of the system. And last, we have quantum computer threat. Well, basically, ECC is currently resistant to attacks from classical computers, but it may become a little vulnerable to attacks from future quantum computers. Quantum algorithms such as Shor algorithm could potentially break the ECC-based cryptographic systems, but they are currently in a research to develop and address this concern.
Well, now I'm going to talk about the ECC versus the RCA. The ACC and the RSA are both widely used public key encryption algorithms. They are used to secure communication, protect sensitive data, and provide digital signatures. However, there are some significant differences between the ECC and the RSA. First, we can talk about the key size. The ECC offers equivalent security to RSA with shorter key lengths. Then we can talk about the performance. The ECC generally offers faster encryption and decryption operations compared to RSA, especially for shorter case length. This makes ECC more suitable for resource-constrained devices, such as mobile device and Internet of Things devices. Then we can talk about the security. Both ECC and RSA are considered secure if implemented correctly. However, ECC is based on the difficulty of solving elliptic curve discrete logarithm problems, while RSA is based on the difficulty of factoring large compositive numbers. The security of ECC relies on the choice of elliptic curve parameters, and the potential for attacks is highly dependent on the specific implementation. Then we can talk about the patent and the licensing. RSA was patented until 2000, please, sorry, while ECC does not have any patent restrictions. This means that ECC can be freely used without any licensing issues. Then we also can talk about the adoption. The RSA has been in use for a longer period and is more widely adopted in various cryptographic applications. However, the ECC is gaining popularity, particularly in modern systems where efficiency and performance are crucial. Ultimately, the choice between the ECC and the RSA depends on the specific requirements and constraints of the system in which they will be used. ECC is often favored for resource-constrained environments, while RSA remains a solid choice for many traditional cryptographic applications. So, in this case, it's important to note that both algorithms can provide strong security when implemented correctly.
Okay, now finally, we are going to talk about when to use it. As we saw before, its main characteristic is that it can achieve the same level of security as other algorithms, but with significantly smaller key sizes. And we can see the table in the next page that the ECC key size is very small in comparison with the RSA. So it comes ideal in, and we can go to the next slide, please. It comes ideal to use this algorithm in mobile devices such as smartphones and tablets, and well as devices of IoT, because these devices typically have resource constraints, like processing power and storage and other things. So ECC provides a lower computational storage and without compromising the security issue. Additionally, this encryption method has been used in the field of cryptocurrencies. For example, Satoshi Nakamoto found that the length of many keys would become very problematic when sharing them, especially when using when using them in mobile devices or simply writing them down in a paper. In this regard, ECC, especially the ECDSA, I think, standard, is using in the field of cryptocurrencies. And last one, in the previous, thank you, is recommended to use it in embedded systems. These systems requires an encryption algorithm that makes them more efficient, and ECC proves to be a suitable option for this regard. Now, in some more specific uses, are security protocols like HTTPS, TLS, SSL, VPN, and email protocols like MIME. Also in Bitcoins, like we said before, specifically in his ECDSA protocol. Also in smart cards and security devices such as electronic identification cards, electronic passwords, and security tokens. In protocols like MIV, that MasterCard, Europlay, and Visa use them, and security protocols for mobile networks like 3G, 4G, and 5G. And I think that's all the presentation.
Finally, as mentioned before, we're going to go over some additional concepts that have to do with this ECC. Well, some of them are the key exchange protocols that, well, as we mentioned before, they can vary the key exchange protocols, such as ECDH, which is the Diffie-Hellman, and the ECIES, which is the curve integrated encryption system. There are also the pairing-based cryptography, which is a mathematical operation that can be performed on elliptic curves. The homomorphic encryption, which is a technique that enables computations to be performed on this encrypted data without having to decrypt it. The side channel attack resistance, which is when side channels attack, exploit this information. Well, this has some sort of restraints or some sort of resistance for these side channels attacks, such as constant time implementations, power analysis, countermeasures, and masking. Then there is the post-quantum ECC. Well, as mentioned by one of our teammates, it becomes with quantum computers, in which the ECC implementations may become vulnerable to attacks. Then the efficient implementation techniques, which is optimization and efficient implementations, are crucial for the practical deployment of ECC. and some standardization efforts. Various organizations, including the National Institute of Standards and Technology, which is the INST, have developed standards for and specifications for the ECC. And it is worth noting that the concepts mentioned above represent advanced aspects of elliptic curve cryptography, and implementing them correctly and securely requires expertise and a deep understanding of the mathematics and cryptographic principles. And that would be all for the presentation. Thank you so much.